Hello students, I welcome you all for the online lecture series of design of steel structure. So in today's lecture we will be studying the design of beam. The question for the today's lecture is design a simply supported beam of effective span 4 meter carrying a factored load of 350 kN at a mid span. The section is laterally supported throughout the span. Design the cross section using I section. Use steel of grade Fe 410. So this is the statement of our numerical. According to our statement, this is the diagram for the numerical. The span of the beam is 4 meter and it carries a concentrated load at the middle of the section. So then the given data, span L is 4000 mm, PU, here the factor load is given, that's why the load is directly ultimate load of 350 kN at the mid span. Fu is 410 MPa, Fy is 250 MPa. Gamma M0 calculated from table number 5 is 1.1. So step number 2 is to calculate the maximum shear force and bending moment. Then we have to calculate the maximum shear force by the formula Vu is equals to Pu divided by 2, as it is simply supported beam carrying the concentrated load at the midpoint. So shear force will be W by 2 and moment is maximum bending moment Mu is equals to Pu, that is ultimate load, into L divided by 4, which is nothing but WL by 4, and it is equals to 350 kilonewton meter. Then we have to plot the shear force diagram, and it is as shown. Here the reaction of 175 kilonewton, again it goes bottom, and 175 kilonewton negative. And thereafter we have to draw the bending moment diagram, and it is in this shape. The third step is to equate maximum bending moment with the yield strength of the section. So MD is equals to Mu, and therefore we have to calculate the ZP required, and the ZP required is equals to Mu into gamma M0. Here value of Mu is 350, gamma M0 is 1.1 divided by Fy, and therefore the ZP required is 1.54 into 10 raised to 6 mm cube. Then select the section from IS 800 annexure H having plastic section modulus greater than above calculated value. Students, note that in the case of compression member and tension member, the sections were selected according to the area, whereas in the case of flexural member, the sections are selected according to the plastic section modulus. That too, all the sections are selected from the annexure H of IS 800 2007. So we will be trying IS LB, that is Indian Standard light beam section of 500 mm depth, about 75 kg per meter. Then from the still table we have to calculate the or write down the following properties. H, that is the depth of the section, 500 mm. Bf, which is equals to 180 mm, that is the width of the flange. Tf, thickness of the flange, 14.1 mm. Tw, which is equals to 9.2 mm, that is the thickness of the web. Izz is equals to 3854 into 10 raised to 4 mm raised to 4, that is Ixx. H1 is 430.2 mm. Then we calculate the ZP or we have to select the ZP, and the ZP of the section selected is 1773.37 into 10 raised to 3 mm cube, which is greater than 15400 into 10 raised to 3 mm cube. And from the steel table only we get the value of ZE, which is equals to 145.2 into 10 raised to 3 mm cube. Note that we have to select the section according to the value of ZP, not according to the value of ZE. Many of the students get confused in the ZP and ZE. The third step is to classify the cross section. According to the table number 2 of IS 800-2007, we have to classify the section. Flange classification, BF upon TF. Here in the case of I section, the BF is taken as BF by 2 and thickness of the flange divided by the thickness of the flange, and it is less than 9.4 epsilon. Therefore, the flange is plastic. Then the web criteria, H1 upon TW. How to calculate this H1 we have learned in the classification of cross section lecture. Here the value of H1 is 430.2 and divided by 9.2, that is width of the flange, and it is 46.76 epsilon, and it is less than 84 epsilon. Hence our web is also plastic. Now as our flange is plastic, web is plastic, hence our section is also plastic, and therefore our value of beta B is equals to 1. Then our fourth step is to calculate the design shear strength of the section. Clause number 8.4.1 of page number 59 gives us the formula for the formula to calculate the VD, that is the design shear strength of the section. VD is equals to FYW into AW divided by root 3 gamma m0. Now value of FYW is 250, AW is equals to 500 into 9.2, that is the here this 500 into 9.2 is nothing but the depth of the section into width of the web. Means here AW is area of the web. Suffix A, suffix W resembles the area of the web, and therefore divided by root 3 gamma m0 is 1.1 and it is 603.6, which is greater than our VU. Therefore beam is safe in the shear. Now we have to check whether the beam is subjected to high or low shear condition. If 0.6 VD, first we have to calculate 0.6 VD. 0.6 into VD is 603.6 kilonewton and it is equals to 632.16 kilonewton, and it is greater than VU, then it is a case of low shear. If it was less than VU, it would be the case of high shear. Then depending upon this case of low shear and high shear, we have to calculate, or we have to design the bending strength of the section, and it is calculated from clause number 8.2.1.2, page number 53. So here beta b md is equals to beta b into zp into fy upon gamma m0. We have to substitute the value of beta b as 1, as our section is plastic. Then we have to substitute zp of the section. We here note that the zp of is section which we have selected should be written in the given formula, not the value of zp required should be written, and into fy is 250 divided by gamma m0 is 1.1. Hence our value of md is 402.95 kilonewton meter, which is greater than mu. Hence our beam is safe in the bending. Then design checks. First one is for the check of web buckling. Students, note that we have to check the beam for the web buckling as well as for the web crippling. The formula for web buckling is FWB, that is web buckling force for the web buckling. WB means web buckling, which is equals to B into TW into FCD. Now assume the stiffness bearing length B is equals to 120 mm. So B is equals to, small b is equals to 120 mm. Therefore capital B is equals to 120 plus h1 by 2. So 120 plus h1 we have calculated in the classification of the cross section, divided by 2, which is equals to 335.1 mm for the end reaction, and TW is equals to 9.2 mm. FCD depends on the slenderness ratio lambda, which is equals to 2.45 into h1 upon TW, and the value is equals to 115, approx 115. Hence, dear students, keep in mind we are considering your wave will be acting as an column. As in the case of column, we used to calculate the lambda is equals to KL upon R minimum. Here also similarly we calculate the value of lambda over here, and then from the table number 9C, page number 42, for Fy is equals to 250 MPa, we have calculated the value of FCD as 89.15 MPa, and then substituting all this given data in the formula of FWB, which is equals to beta B into TW into FCD. So our value of FWB is equals to 274.84 kilonewton, which is greater than Vu. Hence our beam is safe in the web buckling. Then the check for the web crippling, which is equals to FW is equals to AE into FYW divided by gamma m0. FYW is equals to 250 MPa. Then AE is equals to B1 into TW. B1 is equals to B plus N1 into TW, and value of N1 is nothing but the 2.5 into TF plus R1. TF means thickness of the flange, R1 is root radius, TW is thickness of the web. So after substituting these values in the given formula, we get the value of AE as 1819.3 mm square. Then we comes towards the FW, that is the force for the web crippling, is equals to AE into FYW divided by gamma m0. Hence our value for FW is equals to, substituting these values in the formula, our value of FW is equals to 413.47 kilonewton, which is greater than Vu. Hence our beam is safe in the web crippling. Then the last check, that is the check for the deflection. As the beam is safe, as the beam is loaded by a central point load, the deflection due to external working load delta actual is equals to pi pl cube upon 48 ei. Then we have to substitute these values in the formula and we get the deflection of 4.03 mm. The maximum deflection as allowed as per IS 800 2000, that is delta limit is equals to span upon 300 to span upon 240. So this value is in between 13.33 mm to 16.67 mm. Hence, as our actual deflection is less than delta limit, our beam is safe in the deflection. Therefore, ISLB about 75 kg per meter can be used for the given loading on the beam, as it is safe for all the check. Thank you for watching the video. In next lecture, we will be solving another numerical on design of laterally unsupported beam. Till then, keep watching and subscribe the channel. Thank you.